Welcome to the Deep Dive. We're the show that takes complex stuff and, well, makes it make sense fast, helping you get those real aha moments. Today, we're jumping into something fascinating, the hidden world of mechanics of materials. We're talking about how engineers look inside structures to see invisible forces. You know, the thinking behind how a huge skyscraper beam or even a tiny bolt actually works.
That's exactly it. Think of this as a shortcut, really. We're pulling out the core ideas from foundational engineering principles. It helps you understand how something simple, like a steel rod, can handle incredible forces safely. It's critical science for pretty much everything built around us.
Right, so our mission today, decode that silent language of structures, show you the elegant logic engineers use for stability. We want to leave you with a totally new way of seeing the world. We'll unpack some surprising facts about how materials behave, the ingenuity behind it all. Okay, let's unpack this. So first things first, what is mechanics of materials, fundamentally? Well, at its heart, it's about looking inside solid things to understand what happens when you apply forces. Think about it. You push or pull something. That creates reactions inside it. We talk about stress, which is like the intensity of that internal force spread over an area, how strong it feels inside the material. And then there's strain. That's about how much the material actually deforms, how it changes shape.
And this isn't just theory, right? It's vital.
Absolutely vital. For designing anything that needs to hold up, so many engineering codes, safety rules, they're built right on these ideas.
And it's got history, too. It's not some brand new field. The roots go way back, actually.
Yeah.
Early 17th century. Thinkers like Galileo.
Galileo, wow.
Yeah, he was actually doing experiments, trying to figure out how loads affect rods and beams. It was kind of the start of moving engineering from just intuition to, a science you could measure. Then later, early 19th century France, you had a real powerhouse group. Saint-Venant, Poisson, Lemay, Navier. They really built up the theory and the math we still use.
So it evolved from there.
Definitely. As the basic problems got solved, it branched out into more advanced stuff like theory of elasticity, how things spring back, and theory of plasticity when things deform permanently. Nowadays, solving the really tough problems needs serious math and computer power.
Okay, so before we get inside the materials, we need to talk about the foundation, right? Statics. This is where engineers start, making sure things don't just move or fall over. It's all about balance, isn't it?
Yeah.
Here's where it gets really interesting.
Exactly. Balance is the key word. Now, when forces act on something, they usually fall into two main types. First, surface loads. These make direct contact. Could be a tiny point force or spread out like snow on a roof.
Right, like that snow load. And engineers have a neat trick for that, don't they? For those distributed loads. They can sort of boil it down to one single force, a resultant force. And the size of that force is just the total area under the load shape. And it acts right through the geometric center.
That's the one. It simplifies a complex load into something manageable. Very useful. The second type is body forces. These act without touching. Gravity is the classic example. An object's weight always acts through its center of gravity.
Like a crane lifting something heavy, gravity's pulling on it constantly.
Precisely. Then, besides the loads, you have the supports, how the structure is held up.
Yeah.
And the rule is simple. If a support stops movement in one direction, it pushes back with a force in that direction. If it stops rotation, it pushes back with a rotational force, a moment.
So like a wheel support, a roller. It only stops up and down movement.
Right, so it only exerts a vertical force.
Yeah.
But something like a concrete footing, a fixed support, it stops movement side to side, up and down, and rotation. So it develops multiple forces and a moment.
And to make sure it all stays put, stays rigid, that's where the equations of equilibrium come in. They sound simple, but they're powerful. Sum of forces equals zero.
No acceleration, no translation.
And sum of moments equals zero.
No spinning, no rotation. Yeah, these are really the bedrock. For 3D, you balance forces and moments in X, Y, and Z. For 2D, it's simpler. Balance horizontal forces, vertical forces, and moments around a point. And this raises an important question. Why do these equations matter so much?
Because they're non-negotiable. Right.
Yeah.
If these aren't satisfied, the thing just won't be stable. It won't work.
Exactly. It has to balance.
Which brings us to the crucial first step, drawing that free body diagram, the FBD. It's not just a quick sketch, is it? It's like a map. You have to account for every force, every moment, known and unknown.
Yeah.
Trying to solve without it is like working blindfolded.
Absolutely. Now, statics tells us about external forces, but its real power here is letting us figure out the internal forces, what's happening inside. We use this technique, the method of sections. Imagine you take your beam or column, whatever, and you make an imaginary cut right through the spot you're interested in. You slice it in two, conceptually. Then you draw a free body diagram of just one of those pieces.
Ah, I see.
The forces you draw at the cut, those are the internal forces. They show how the material on one side is basically holding on to the other side.
Okay, so you make this imaginary cut. What kinds of forces pop up there? You said there are four main types.
That's right.
Okay, so first, normal force, N, perpendicular to the cut, pushing or pulling.
Yep, like tension in a rope or compression in a column.
Then shear force, V, that's parallel to the cut, trying to slide things sideways.
It's like scissors cutting paper, exactly.
Got it. Then torsional moment or torque, T, that's a twist.
Around the long axis. Think twisting a screwdriver.
Okay, and finally, bending moment, M. That's what makes things bend, like a diving board.
That's the one. These four N, V, T, and M tell you the complete picture of what the material is feeling internally at that cut. And it's worth adding, for simpler cases, like forces all in one plane, you often just worry about normal force, shear force, and bending moment. Torque might not be in the picture.
So there's a process for finding these, a procedure for analysis. Step 1, figure out the external reactions on the whole thing if you need to.
Usually, yeah.
Then the key step, draw the free body diagram of your cut piece, show the unknown NVMT right at the cut.
Right at the centroid of the cut surface, ideally.
And then apply those equilibrium equations to that cut piece to solve for the unknown.
Exactly. And a good tip. Summing moments at the cut often simplifies things. It can let you solve for M and T directly.
And if you guess the direction wrong on your diagram and the answer comes out negative?
No problem. It just means the real force or moment acts in the opposite direction to what you drew. The math tells you. It's a systematic way to map out everything happening inside.
Okay, internal forces mapped out. Now let's zoom in on stress.
Right. And what's fascinating here is how we go from that total internal force, like N or V, to an intensity, force per unit area. Stress is that intensity. And we usually assume the material is, well, solid, continuous, no gaps, and cohesive. It all holds together.
So it lets you predict behavior regardless of the total size.
That's the power of it. It's a universal measure of how hard the material is working internally.
Okay, and you mentioned two main types. Normal stress, that's the force intensity perpendicular to the surface.
Correct.
And it can be tensile, pulling it apart, or compressive, squashing it together.
Exactly. Stretching versus crushing, basically.
And the other is shear stress. That's the force intensity parallel to the surface, like trying to slide layers past each other.
Spot on. Tensile is pulling, shear is sliding.
So tearing paper is tensile, cutting with scissors is shear. Got it.
And sometimes, especially in complex 3D situations, engineers imagine a tiny cube inside the material. You look at the stresses on all 6 faces of that cube to get the full picture, the general state of stress at that point. It helps break down complexity.
Makes sense. What about units? Force per area. Newtons per square meter. That's a Pascal, right?
It is, but a Pascal is tiny, so small. Engineers almost always use kilopascals, kPa, megapascals, MPa, or gigapascals, GPa.
A million, gigabillion.
Right, and a handy conversion. 1 Newton per square millimeter equals 1 megapascal. You see MPL a lot.
Okay, let's make this practical. Average normal stress in an axially loaded bar, like pulling out a rod. For the stress to be nice and uniform, evenly spread out, you need some conditions.
You do. The bar should be prismatic, same cross-section all along.
Okay.
The material needs to be homogeneous, same stuff everywhere, and isotropic, same properties in all directions. Steel often behaves like this. Wood, not so much. It has grain.
And the load, applied right down the middle, through the centroid.
Critical. If all that holds, then the stress is uniform. And the formula is simple. Average normal stress, sigma, equals the internal force N divided by the area A.
And N is just the external pull P in this case.
For a simple axial load, yes. We call this uniaxial stress, just stress in one direction. Fundamental stuff.
So if a real part has, say, different thicknesses or different loads along its length, you'd figure out the internal force N in each section.
Yep.
And the highest stress happens where that NA ratio is biggest, usually the thinnest spot or the spot with the highest internal force.
That's exactly where you look. Find the maximum NA. That's your critical section, your potential weak link.
Like in a steel tie rod holding something up, it's designed for that tension.
Precisely. Now, what about average shear stress? We see this clearly in direct shear. Think of a punch going through a plate or a bolt connecting 2 overlapping pieces. The force is trying to slice the material.
Okay.
The formula is similar. Average shear stress, tau, equals the internal shear force, V, divided by the shear area, A. Tau G equals VA.
So V is the slicing force, A is the area resisting the slice. And you see this a lot in pins and bolts, like in machinery you mentioned a tractor linkage.
Very common. And a pin can be in double shear.
Double shear, meaning
Meaning the force is trying to shear the pin across two cross-sections simultaneously.
okay. So the load gets split.
Exactly. Which means the stress on each shear plane is half of what it would be in single shear, where the force cuts across only one plane. It's a way to make connections stronger.
Clever. So same pin, same force, but double shear is safer.
All else being equal, yes, lower stress. And there's a neat detail here, the complementary property of shear. If you have shear stress on one face of that tiny imaginary cube inside the material,
Yeah.
equilibrium demands that you must have equal shear stresses on the adjacent faces to balance things out. It creates a state called pure shear.
So stresses are always interconnected.
They are. It's a balanced system internally. Fascinating, isn't it?
It really is. Okay, so we understand forces, internal loads, stress. How do engineers use all this to actually design things safely?
Yeah.
You mentioned allowable stress design, ASD.
Right. ASD is a very common approach.
And the core idea is, don't push the material to its absolute limit. Build in a safety margin.
That's the essence of it. You restrict the stress allowed in the design to be significantly less than the stress that would cause failure.
Why? Because the real world isn't perfect.
Exactly. You've got uncertainties everywhere. Maybe slight flaws in manufacturing, unexpected vibrations, materials degrading over time, rust, decay. Plus, material properties themselves aren't perfectly uniform, especially for things like wood or concrete. So you need a buffer.
And that buffer is a factor safety, FS.
Precisely. It's defined as the ratio of the failure load or stress to the allowable load or stress you're using in your design.
So FS, failure stress.
Yep.
Allowable stress.
Yep. And the value chosen depends hugely on the application. Yeah. Aircraft might use an FS close to 1 because weight is paramount.
But something critical like in a nuclear plant.
Could be 3 or even higher. Bigger uncertainties, much bigger consequences of failure. Design codes specify these factors.
So in ASD, the math becomes pretty direct. If you know the internal force, NRV, and the allowable stress, locale or talo, from the code, you just calculate the area you need. Area equals force allowable stress.
That's the basic calculation. A equals N salo, or A equals V telo. It tells you how big that column-based plate needs to be, or what diameter bolt you need. Very practical. Now, while ASD is reliable, there's a more, let's say, sophisticated method gaining traction. Limit state design, LSD, or often called load and resistance factor design.
LRFD.
Okay, LSD or LRFD. How's that different?
It takes a more statistical approach. Instead of one big factor of safety covering everything, it separates the uncertainties. It looks at the probability of loads being higher than expected and the probability of the material being weaker than expected separately.
So it's more nuanced. It is. If we connect this to the bigger picture, it's about building with intelligent confidence, using statistics to refine the safety margins based on where the uncertainty lies. LRFD uses load factors. These are numbers greater than 1, applied to different load types. A predictable dead load, like the building's own weight, might get a factor of, say, 1.2. But a variable live load, like people or snow, might get 1.6, reflecting more uncertainty. Codes give combinations, like 1.2 times dead load plus 1.6 times live load.
Gotcha. So you inflate the loads based on how predictable they are.
Right. And then on the other side, you have resistance factors. These are numbers less than 1, applied to the material's calculated strength.
Okay, so you reduce the strength.
You reduce the nominal strength to get a reliable design strength. Steel in tension might have a fuller 0.9 because steel is very predictable. Concrete, being more variable, gets a lower ref. It reflects confidence in the material.
So the LRFD rule is the factored strength has to be bigger than the factored loads.
That's the criterion. Times nominal strength must be greater than or equal to the sum of Wookai's loads. Wookai Vanier Kyrie.
It sounds more complex, but it targets the uncertainties better.
Exactly. It often leads to more efficient designs while maintaining safety because it's based on a better understanding of probabilities. It's where a lot of modern structural design is heading.
Wow. Okay, so that brings us full circle. From basic forces through internal stresses, all the way to these sophisticated design methods like LRFD. We've really unpacked how engineers ensure things stay standing. Hopefully, this deep dive has cut through some complexity, giving you that new lens for seeing the built world.
Absolutely. It's quite something to realize the amount of thought and calculation that goes into even simple connections. It's not just putting parts together, it's managing forces, understanding materials down to their core. So the next time you step into a building, cross a bridge, or even just tighten a bolt, what new appreciation will you have for the hidden forces and meticulous design principles that keep it all standing strong and safe?
Great question to ponder. Thank you for joining us on this deep dive. Keep that curiosity alive and keep exploring the fascinating world around you.